Okay guys, for this last video for 7.2, we're actually going to be integrating with respect to y. And let's take a look and see why that is. So in example 5, it wants us to find the area of the region bounded by these curves, this curve, and these two horizontal lines. Fortunately, the graph is shown here, which is very helpful. So what I want you to notice is that x is described in terms of y, not the other way around. So we have x equaling y squared. X is a function of y. And we're going to cap that off on the top at 3 and on the bottom at -1. So notice like the cutoffs are actually going top to bottom instead of left to right. And the function is going left to right instead of top to bottom. So when you're integrating with respect to y, here's the general formula. So when integrating with respect to y, the formula would go, you would integrate from the bottom point of intersection to the top point of intersection, and then you would do the curve that's on the right curve minus the left curve. So it goes right to left, and then dy. So that's when you're integrating with respect to y. So if you notice here, we'll still do the same steps, but I'm going to find the y values of the points of intersection instead of the x values, because we're integrating now from bottom to top. So in this case, that would be y equals -1 and y equals 3. And they're not really points of intersection, they're just sort of where these lines are cutting off this curve. Okay, then step 2, we decide which curve is on the right as opposed to the left. So we could say that x equals y squared is always the one on the right because it's greater than the, actually the whole graph is always on the right. And basically it's greater than the y-axis, greater than when x is 0, greater than the y-axis. So then step 3 would just be to set up the integral. So we're going to integrate from the bottom point to the top point, and then we're going to do the right curve, which is y squared, minus the left curve, which basically was the y-axis, which is when x is 0. And then we're integrating with respect to y. So this ends up equaling basically y cubed over 3 from -1 to 3, which ends up equaling 27 over 3 minus -1 over 3. So that ends up equaling 28 over 3. So it's the same steps, but when you're finding points of intersection, you're finding y values. So you're looking from bottom to top, and you're integrating from bottom to top. And when you're checking to see which curve is greater, if it's further on the right, that makes it greater. Okay, so here's another example, which again, fortunately, they have the region there for us. So we need to find these points of intersection. Now, fortunately, they're showing us that that's 1, but I kind of want to show you how we would find those if it wasn't showing us. So we're going to find points of intersection, and specifically the y values of the points of intersection. So we set the two equations equal to each other. We set the 12y squared minus 12y to the third equal to 2y squared minus 2y. And I'm just trying to solve this for y, so I need a factor. First, let me just get everything on one side. And maybe I'll put this in descending order. So we have -12y to the third. I'll subtract over the 2y squared, so we'll have plus 10y squared. And I'll add over the 2y. And this is all equal to 0. Then I'm going to factor out a -2y to make the factoring easier. So I'll have 6y squared minus 5y minus 1. And then I need to factor this a little bit further. So I'll have 6y and y, because that together would make 6y squared, and then 1 and 1. because 1 times 1 is 1. And then if I make this one negative, then these terms would make negative 6y. This would make positive y. So negative 6 plus 1 would give me negative 5. So our 3 points of intersection would be when y is 0, when y is negative 1/6, and when y is 1. We can throw out the negative 1/6 because we're just going from 0 to 1. The negative 1/6 would be down here, so we can just throw that out. So our points of intersection would be 0 and 1. Okay, then step 2, we can basically look at the graph and see that the 12y squared minus 12y cubed is more to the right. So it's going to be greater than the 2y squared minus 2y. Okay, so then step 3, we set up the integral, which as you can see, I haven't left myself much room. But it's basically going to be, we're going to integrate from 0 to 1, the bottom to the top, of the further right function, so the 12y squared minus 12y cubed, subtract the further left, so the 2y squared minus 2y with respect to y. Okay, so it looks like I'm going to need to move over to the back. So let's rewrite that again. So we have integral from 0 to 1 of the 12y squared minus 12y cubed, and then minus 2y squared minus 2y. And then we're integrating that with respect to y. So that turns out to be the integral of 10y squared minus 12y cubed plus 2y dy. And then that's from 0 to 1. So the antiderivative would be 10y cubed over 3 minus 12y to the 4th over 4 plus 2y squared over 2. Integrate from 0 to 1. And if, with a little simplifying, we have 10/3 y cubed minus 3y to the 4th plus y squared. Evaluate from 0 to 1. So we'll plug 1 in there, and we'll get 10/3 minus 3 plus 1, and then minus 0, basically. So that's 10/3 minus 2, which is 3 1/3 minus 2, which is 1 1/3. So that is the area between those two curves. Okay, so our last but not least example is example 7, where they didn't give us a graph, so it might help us to sketch the graph. But you know what, let's see if we can do it without. If we can't, we'll sketch it, but let's see if we can do it without. So step 1 would be to find points of intersection. So I'd set these two equal to each other. So I would set y plus 2 equal to y squared. That equal to that to figure out the y values that they have in common. So then I would subtract both of those because I want to be able to factor, and I like having my first term positive. So I'd get y plus 1 and y minus 2, because then I'd have negative 2 plus 1 would give me negative 1. So my points of intersection are going to be from negative 1 to 2. Then I have to figure out which one of these curves is greater between those two numbers, between negative 1 and 2. So I guess I could test a point. Man, okay, we're going to have to go on the back again. Or I can maybe fit that over here. So step 2, we're going to test a point between negative 1 and 2. So 0 is an easy one. So test 0, y equals 0. So I'll plug 0 in there. So 0 plus 2 is equal to 2, and I'll plug 0 in there. 0 squared is 0. So the y plus 2 is greater than the y squared between negative 1 and 2. Okay, so that's how we determine which ones, or further right anyways. This one's further right. Okay, so then step 3 we'll do on the back. And since I used all this, we'll have to actually go up here. Okay, so for step 3, we basically integrate from bottom to top. So I believe we were going from -1 to 2. So -1 would be the lower one. So -1 to 2 of the curve that's further right minus the other curve, dy. Okay, and so then I have to find the antiderivative, so that would be y squared over 2 plus 2y minus y cubed over 3, and then I'm integrating that from -1 to 2. So that would be 2 squared over 2 plus 2 times 2 minus 2 cubed over 3 minus 1/2 plus minus 2. So that's -1, so minus 2 and then plus 1/3. Okay, so then that equals 2 plus 4 minus 8/3 minus 1/2. Oh, minus 1/2. I think that was a minus 2 before. Yeah, but then it becomes plus 2 and then minus 1/3. So I like to combine my quote like terms. So I'm going to have 2 plus 4 plus 2 is going to make 8. And then -8/3 minus 1/3 is going to make -9/3. And then minus 1/2. And then this becomes 3. So I have 8 minus 3 is 5. Minus 1/2 is 4.5. Okay, and that's our final answer for example 7. So again, if you have questions, please come see me in tutorial tomorrow, Tuesday. And these are the problems that we'll be working on in class. See you there.